Good morning, students. Myself Harjinder Singh, lecturer mechanical from Government Polytechnic College, Batala. Let us start one important topic of thermodynamics too, that is IC engine testing. Introduction. The basic task in the design and development of engines is to reduce the cost and improve the efficiency and power output. In order to achieve the above task, the development engineers has to compare the engine developed with other engines in terms of the output and efficiency. Toward this end, he has to test the engine and make measurement of relevant parameters that reflect the performance of the engine. IC engine generally operate within a useful range of speed. Some engines are made to run at fixed speed by means of speed governor, which is rated speed. The performance of the engine depends upon the interrelationship between the power developed, speed and the specific fuel consumptions at each operating conditions within the useful range of speed and load. The following factors are to be considered in evaluating the performance of an engine. First, maximum power or torque available at each speed within the useful range of speed. Second, the range of power output at constant speed for stable operations of the engine. The different speed should be related at equal interval within the useful speed range. Third, the brake specific fuel consumption at each operating condition within the useful range of operation. Fourth, the reliability and durability of the engine for the given range of operation. Purpose of testing an IC engine. In general, the purpose or significance of testing an IC engine is to determine the following. Number 1, to determine the rated power output with respect to the fuel consumption in kg per kilowatt hour of the brake power output. The second purpose for testing is to determine the mechanical and thermal efficiencies of the engine. Third, to see the performance of the engine when loaded at different loads. Fourth, to determine the quantity of lubricating oil required per BP kilowatt hour. Fifth, to determine the quantity of cooling water required per BP kilowatt hour. Sixth one, to determine the overall load carrying capacity of the engine. Next is to prepare the heat balance sheet of the engine. Some important terms as per ISI standards. First, speed. The speed of an engine is the mean speed of its crankshaft in revolutions per minute, except in case of free piston engines where the speed is the number of cycles per minute of the reciprocating components. Second, steady load speed band. It is a maximum total variation in speed expressed as a percentage of the mean speed, which may occur while there is no change in external load conditions. Third is continuous power. The power which the engine is capable of delivering continuously between the normal maintenance intervals stated by the manufacturer at stated speed and under stated operating conditions. Fourth, indicated power. It is the total power developed in the working cylinder by the gases on the combustion side of the working piston. Fifth is friction power. It is the power consumed in frictional resistance. Brake power. It is the total power measured at driving shaft. Fuel consumption. The quality of the fuel consumed by the engine per unit time of the stated power and under stated operating conditions. Next is specific fuel consumption. It is the quantity of the fuel consumed per unit of power per unit of time. It is generally expressed in grams of fuel consumed per kilowatt hour or BHP upon BP. Standard operating conditions. The following are the standard operating conditions. First, mean barometric pressure. It is taken as 736 mm of mercury. Second, intake air temperature. It is taken as 300 degree Kelvin or 27 degree centigrade. Engine power. The energy flow through the engine is expressed in three distinct terms. They are indicated power, that is IP, friction power FP, and brake power, that is BP. The indicated power can be computed from the measurement of forces in the cylinder and the brake power from the measurement of forces at the crankshaft of the engine. The friction power can be estimated by monitoring the engine or from the difference between IP and BP, that is FP friction power is equal to indicated power minus brake power. Indicated mean effective pressure. It may be defined as the constant pressure acting over the full length of the stroke and capable of producing the same amount of work as is actually produced during the complete cycle of the engine. It is generally denoted by PIM or IMEP, indicated mean effective pressure. As the pressure in the cylinder varies throughout the cycles and variation can be expressed with respect to the volume or crank angle rotation to obtain PV or P theta diagram respectively. However, such a continuous variation does not readily lend itself to simple mathematical analysis in the computations of IP. If an average pressure for one cycle can be used, then the computation becomes far less difficult. Referring figure, as the piston moves back and forth between TDC to BDC, the process lines on the PV diagram indicated the successive states of the working fluid throughout the cycle. The indicated network of the cycle is represented by the area 1, 2, 3, 4. Here 1, 2, 3 and 4. Enclosed by the process lines for the cycle. If the area of a rectangle ABCD equals the area 1, 2, 3, 4, the vertical distance between the horizontal line AB and CD respectively gives the indicated mean effective pressure IMEP. Indicated mean effective pressure, it is mean value expressed in Newton per meter square, which when multiplied by the displacement volume or swept volume versus give the same indicated network as is actually produced with the varying pressure. PIM multiplied by V1 minus V2 is equal to network of cycle. PIM is equal to net work of cycle divided by V1 minus V2. Also PIM is equal to area of indicator diagram multiplied by spring number divided by length of the indicator diagram, A multiplied by S divided by L. If A is equal to area of indicator diagram in centimeter square and L is equal to length of the indicator diagram in centimeter and S is equal to spring number or spring strength in Newton per meter square per centimeter, then PIM is equal to A multiplied by S divided by L Newton per meter square. The value of the area measured when divided by the piston displacement and multiplied by the spring number of the indicator, the result in the mean ordinate or indicated mean effective pressure, that is PIM. Next is brake mean effective pressure. It may be defined as the mean effective pressure acting on the face of piston, which would develop brake power equivalent to that during actual varying pressure conditions. It is generally denoted by PBP or BMEP, brake mean effective pressure. Friction mean effective pressure is the portion of mean effective pressure which is required to overcome friction losses, and brake mean effective pressure is the portion which produces the useful power delivered by the engine. PIM is equal to PFM plus PBM. Also, brake power PB is equal to PBM multiplied by LANK divided by 60,000 kilowatt, where PBM is equal to brake mean effective pressure in Newton per meter square. Here L is equal to length of stroke in meter, A is equal to area of piston in meter square, N is equal to number of working strokes per minute, K is equal to number of cylinders of the engine. Mechanical efficiency is equal to BP upon IP, that is PBM divided by PIM. Piston speed, it is the average or mean distance travelled by the piston of the engine in 1 minute, that is piston speed is equal to 2 ln meter per minute, where L is equal to length of stroke in meter and N is equal to revolutions per minute of the crankshaft. Fuel air or air fuel ratio. The relative proportion of the fuel and the air in the engine are very important from the standpoint of combustion and efficiency of the engine. This is expressed either as a ratio of the mass of the fuel to that of the air or vice versa. In the SI engine, the fuel air ratio practically remains constant over a wide range of operation. In CI engines, at a given speed, the air flow does not vary with load. It is the fuel flow that varies directly with load. Therefore, the term fuel air ratio is generally used instead of air fuel ratio. A mixture that contains just enough air for complete combustion for all the fuel in the mixture is called chemically correct or stoichiometric fuel air ratio. A mixture having more fuel than that in chemically correct mixture is termed as rich mixture, and a mixture that contains less fuel or excess air is called lean mixture or weak mixture. The ratio of actual fuel air ratio to the chemically correct fuel air ratio is called equivalence ratio and is denoted by phi. Phi is equal to actual fuel or air ratio divided by stoichiometric fuel minus air ratio. Accordingly, if phi is equal to 1, it means it is chemically correct mixture. If phi is less than 1, it means lean mixture or weak mixture, and if phi is greater than 1, it means the mixture is rich mixture. Calorific value. Calorific value of a fuel is the thermal energy released per unit quantity of the fuel when the fuel is burned completely and the products of combustions are cooled back to the initial temperature of the combustion mixture. Other terms used for the calorific value are heating value and heat combustion. When the products of combustions are cooled at 25 degree centigrade, practically all the water vapor resulting from the combustion process is condensed. The heating value so obtained is called higher calorific value or gross calorific value of the fuel. The lower or net calorific value is the heat released when vapor in the product of combustion is not condensed and remains in the vapor form. Measurement of air supply of an IC engine. To measure air supply, the orifice method can be used if pressure pulsation could be damped out by some means. The usual method of damping out the pressure pulsation is to fit an air box of suitable volume, that is 500 to 600 times the swept volume in single cylinder engines and less in case of multi cylinder engine, to the engine with an orifice placed in the side of the box remote from the engine as shown in figure. This is the measurement of air by air box method. Let A is equal to area of orifice in meter cube. CD is equal to coefficient of discharge of the orifice. Delta H is equal to difference of pressure as measured in centimeter of water. MA is equal to mass of 1 cubic meter of air in kg. MW is equal to mass of 1 cubic meter of water in kg. H is equal to head causing flow through the orifice in meter of air. Let V is equal to velocity of air flowing through the orifice in meter per second. Q is equal to discharge of air flowing through the orifice in meter cube per second. Now consider 1 meter cube of air at pressure of P in Newton per meter square and absolute temperature T in Kelvin, then applying gas law. Gas is equal to N, PV is equal to MART, but V is equal to 1 meter cube. Therefore, MA mass of air is equal to P divided by RT. Here MA is equal to P divided by 287 T, because R is equal to 287 joule per kg Kelvin. Now H is equal to delta H divided by 100 multiplied by MW upon MA meter of air. Also V is equal to CD under root 2GH and Q is equal to AV. Therefore, Q is equal to ACD under root 2GH. Now using the equation 1 and equation 2, the mass of the air supplied can be calculated as follows. Mass of air supplied is equal to QMA. Next is air standard efficiency. The air standard efficiency is also known as thermodynamic efficiency. It is mainly a function of compression ratio and other parameters. It gives the upper limit of the efficiency obtained from an engine. For engines working on Otto cycle, the air standard efficiency eta Otto is equal to 1 minus 1 upon R upon gamma minus 1, where R is equal to compression ratio and gamma is equal to adiabatic index. Mechanical efficiency. It may be defined as the ratio of the power obtained at the crankshaft, that is brake power BP, to the indicated power IP. Thus, mechanical efficiency is equal to the ratio of brake power to the indicated power. Mechanical efficiency takes into account the mechanical losses in an engine. The mechanical losses of an engine may be further subdivided into the following groups. First, friction losses, as in case of pistons, bearings, gears, valve mechanisms. With the development in the bearing design and materials, the improvement in gears etc., these losses are usually limited from 7 to 9% of the indicated power output. Second one is power is absorbed by engine auxiliaries such as fuel pump, lubricating oil pump, water circulating pump, radiator, magneto and distributor, electric generator for battery charging, radiator fan etc. These losses may account for 3 to 8% of the indicated output. Third is ventilating or fanning action of the flywheel. This loss is usually below 4% of the indicated output. Fourth is working of charging and the cylinder with fresh charge and discharging the exhaust gases during the exhaust stroke. In case of two-stroke engines, the power absorbed by the scavenging pump etc., these losses may account from 2 to 6% of the indicated power output. In general, the mechanical efficiency of the engine varies from 65 to 80%. Indicated thermal efficiency. It may be defined as the ratio of heat converted into indicated work to heat energy supplied by the fuel during a specified period of time. So, indicated thermal efficiency is equal to heat equivalent to IP, indicated power per minute, to the heat energy supplied by the fuel per minute, IP multiplied by 60 divided by MF multiplied by CV. Here MF is equal to mass of fuel supplied to the engine per minute. CV is equal to lower calorific value of the fuel. Brake thermal efficiency. It may be defined as the ratio of the heat equivalent to the power brake power, that is BP, to the heat energy supplied by the fuel during a specific period of time. So, brake thermal efficiency is equal to heat equivalent to BP per minute divided by heat energy supplied by fuel per minute, BP multiplied by 60 divided by MF multiplied by CV. Here mf is equal to mass of fuel supplied to the engine per minute, and Cv is equal to lower calorific value of the fuel. In modern engines, an indicated thermal efficiency of almost 28% is obtainable with gas and gasoline spark ignition engines, having a moderate compression ratio and as high 36% of even more with high compression ratio diesel engines, that is CI engine. Relative efficiency. The relative efficiency or efficiency ratio, as it is sometimes called, is the ratio of the actual efficiency obtained from an engine to the theoretical efficiency of the engine cycle. So, relative efficiency is equal to actual thermal efficiency divided by air standard efficiency. Relative efficiency for most of the engines varies from 85 to 95%, with theoretical air, and decreases rapidly with insufficient air to about 75% to 90% of air. Volumetric efficiency. The volumetric efficiency is measured of the success with which the air supplied and thus the charge is induced into the engine cylinder. It is very important parameter, since it indicates the breathing capacity of the engine. Volumetric efficiency is defined as the ratio of volume of air induced at ambient conditions to the swept volume, or it may also be defined as the ratio of actual mass of air drawn into the engine cylinder during a given period of time to time the theoretical mass which should have been drawn in during that same period of time, based upon the total piston displacement of the engine and the temperature as well as pressure of the surrounding atmosphere. Here volumetric efficiency is equal to actual mass divided by theoretical mass. Here m theoretical is equal to rho into A multiplied by n into V s. Here rho A is the density of the air, V s is the swept volume, and n is the number of intake stroke per minute. For 4-stroke engine, n is equal to capital N upon 2, and for 2-stroke engines, n is equal to capital N, where n is the speed of the engine in revolution per minute. The actual mass of the measured quantity. The theoretical mass is the computed from the geometry of the cylinder. The number of cylinders and the speed of the engine is connections with the density of the surrounding atmosphere. Volumetric efficiency for the naturally aspirated engine is generally about 75%. Mathematically, volumetric efficiency is equal to volume of air or charge induced during suction stroke at normal temperature pressure, swept volume to the swept volume of the engine cylinder. Determination of indicated and power brake power. In this method, to find out IP, an indicator is used to find out the mean effective pressure. This method is used for slow speed engines. An indicator is an instrument which produces a graphic record for the pressure inside the engine cylinder for every position of the piston as it reciprocates. It consists of small cylinder fitted with a piston, the underside of which is placed in communications with the cylinder. The upper side of the indicator piston is kept in communications with the atmosphere. A helical spring on the top of the piston has one end attached to the piston and other to the cover of the indicator cylinder, through which the passes the piston rod, which carries a pencil at its upper end. This pencil traces out the indicator power PV diagram on the paper. On working with actual engines, it is often